improved as the reinforcements impart their exceptional physical and mechanical properties. The mechanical properties become unavailable from the individual constituent materials by syllogism. At the same time, the designer of product or structure receives options to choose an optimum combination from the variety of matrix and strengthening materials. To shape the engineered composites, it must be formed. The reinforcement is placed onto the mold surface or into the mold cavity. Before or after this, the matrix can be introduced to the reinforcement. The matrix undergoes a melding event which sets the part shape necessarily. This melding event can happen in several ways, depending upon the matrix nature, such as solidification from the melted state for a thermoplastic polymer matrix composite or chemical polymerization for a thermoset polymer matrix. According to the requirements of end item design, various methods of molding can be used. The natures of the chosen matrix and reinforcement are the key factors influencing the methodology. The gross quantity of material to be made is another main factor. To support high capital investments for rapid and automated manufacturing technology, vast quantities can be used. Cheaper capital investments but higher labor and tooling expenses at a correspondingly slower rate assists the small production quantities. Many commercially produced composites use a polymer matrix material often called a resin solution. There are many different polymers available depending upon the starting raw ingredients. There are several broad categories, each with numerous variations. The most common are known as polyester, vinyl ester, epoxy, phenolic, polyamide, polyamide, polypropylene, PEEK and others. The reinforcement materials are often fibers but also commonly ground minerals. The various methods described below have been developed to reduce the resin content of the final product, or the fiber content is increased. As a rule of thumb, layup results in a product containing 60% resin and 40% fiber, whereas vacuum infusion gives a final product with 40% resin and 60% fiber content. The strength of the product is greatly dependent on this ratio. Martin Hub and Lucia consider wood to be a natural composite of cellulose fibers in a matrix of lignin. 48, 49. Cores in composites. Several layup designs of composite also involve a co-curing or post-curing of the prep edge with many other media, such as foam or honeycomb. Generally, this is known as a sandwich structure. This is a more general layup for the production of cowlings, doors, radomes or non-structural parts. Open and closed cell structured foams like polyvinyl chloride, polyurethane, polyethylene or polystyrene foams, balsa wood, syntactic foams, and honeycombs are generally utilized core materials. Open and closed cell metal foam can also be utilized as core materials. Recently, 3D graphene structures, also called graphene foam, have also been employed as core structures. A recent review by Karam and Zuit al. Have provided the summary of the state-of-the-art techniques for fabrication of the 3D structure of graphene, and the examples of the use of these foam-like structures as a core for their respective polymer composites. 50. Semicrystalline polymers. Although the two phases are chemically equivalent, semicrystalline polymers can be described both quantitatively and qualitatively as composite materials. The crystalline portion has a higher elastic modulus and provides reinforcement for the less stiff, amorphous phase. Polymeric materials can range from 0% to 100%, 51. Crystallinity aka volume fraction depending on molecular structure and thermal history. Different processing techniques can be employed to vary the percent crystallinity in these materials and thus the mechanical properties of these materials as described in the physical properties section. This effect is seen in a variety of places, from industrial plastics like polyethylene shopping bags to spiders which can produce silks with different mechanical properties. 52. In many cases these materials act like particle composites with randomly dispersed crystals known as spherulites. However, they can also be engineered to be anisotropic and act more like fiber-reinforced composites. 53. In the case of spider silk, the properties of the material can even be dependent on the size of the crystals, independent of their volume fraction. 54. Ironically, single-component polymeric materials are some of the most easily tunable composite materials known. Methods of fabrication. Normally, the fabrication of composite includes wetting, mixing or saturating the reinforcement with the matrix. The matrix is then induced to bind together, with heat or a chemical reaction, into a rigid structure. Usually, the operation is done in an open or closed forming mold. However, the order and ways of introducing constituents alters considerably. Composites fabrication is achieved by a wide variety of methods, including advanced fiber placement, automated fiber placement. 55. Fiberglass spray layup process. 56. Filament winding. 57. Laxide process. 58. Tailored fiber placement. 59. Tufting. 60. And Z-pinning. 61. Overview of mold. The reinforcing and matrix materials are merged, compacted, and cured, processed, within a mold to undergo a melding event. The part shape is fundamentalized after the melding event. However, under particular process conditions, it can deform. The melding event for a thermoset polymer matrix material is a Curing reaction that is caused by the possibility of extra heat or chemical reactivity such as an organic peroxide. The melding event for a thermoplastic polymeric matrix material is a solidification from the melted state. The melding event for a metal matrix material such as titanium foil is a fusing at high pressure and a temperature near the melting point. It is suitable for many molding methods to refer to one mold piece as a lower mold and another mold piece as an upper mold. Lower and upper does not refer to the mold's configuration in space, but the different faces of the molded panel. There is always a lower mold, and sometimes an upper mold in this convention. Part construction commences by applying materials to the lower mold. Lower mold and upper mold are more generalized descriptors than more common and specific terms such as male side, female side, A side, B side, tool side, bowl, hat, mandrel, etc. Continuous manufacturing utilizes a different nomenclature. Usually, the molded product is referred to as a panel. It can be referred to as casting for certain geometries and material combinations. It can be referred to as a profile for certain continuous processes. Some of the processes are autoclave molding, 62, vacuum bag molding, 63, pressure bag molding, 64, resin transfer molding, 65, and light resin transfer molding. 66, other fabrication methods. Other types of fabrication include casting, 67, centrifugal casting, 68, braiding, onto a former, continuous casting, 69, filament winding, 70, press molding, 71, transfer molding, pultrusion molding, 72, and slip forming. 73. There are also forming capabilities including CNC filament winding, vacuum infusion, wet layup, compression molding, and thermoplastic molding, to name a few. The practice of curing ovens and paint booths is also required for some projects. Finishing methods. The composite parts finishing is also crucial in the final design. Many of these finishes will involve rain erosion coatings or polyurethane coatings. Tooling. The mold and mold inserts are referred to as tooling. The mold/tooling can be built from different materials. Tooling materials include aluminium, carbon fiber, invar, nickel, reinforced silicone rubber and steel. The tooling material selection is normally based on, but not limited to, the coefficient of thermal expansion, expected number of cycles, end item tolerance, desired or expected surface condition, cure method, glass transition temperature of the material being molded, molding method, matrix, cost and other various considerations. Physical properties. Plot of the overall strength of a composite material as a function of upper volume fraction limited by upper bound, isostrain, and lower bound, isostress, conditions. Usually, the composite's physical properties are not isotropic, independent of the direction of applied force, in nature. But they are typically anisotropic, different depending on the direction of the applied force or load. For instance, the composite panel's stiffness will usually depend upon the orientation of the applied forces and forward/or moments. The composite's strength is bounded by two loading conditions, as shown in the plot to the right. Isostrain rule of mixtures. If both the fibers and matrix are aligned parallel to the loading direction, the deformation of both phases will be the same, assuming there is no delamination at the fiber-matrix interface. This isostrain condition provides the upper bound for composite strength, and is determined by the rule of mixtures. Figure A shows the isostress condition where the composite materials are perpendicular to the applied force, and B is the isostrain condition that has the layers parallel to the force. 74, where EC is the effective composite Young's modulus, and 6 and EI are the volume fraction and Young's moduli respectively, of the composite phases. For example, a composite material made up of alpha and beta phases as shown in the figure to the right under isostrain, Young's modulus would be as follows, where V and V are the respective volume fractions of each phase. This can be derived by considering that in the isostrain case, assuming that the composite has a uniform cross-section, the stress on the composite is a weighted average between the two phases. The stresses in the individual phases are given by Hooke's law. Combining these equations gives that the overall stress in the composite is. Then it can be shown that isostress rule of mixtures. The lower bound is dictated by the isostress condition, in which the fibers and matrix are oriented perpendicularly to the loading direction, and now the strains become a weighted average. Rewriting Hooke's law for the individual phases, this leads to, from the definition of Hooke's law and in general following the example above, if one had a composite material made up of alpha and beta phases under isostress conditions as shown in the figure to the right, the composition Young's modulus would be the isostrain condition. Implies that under an applied load, both phases experience the same strain but will feel different stress. Comparatively, under isostress conditions both phases will feel the same stress but the strains will differ between each phase. A generalized equation for any loading condition between isostrain and isostress can be written as SAD/75, where X is a material property such as modulus or stress, C, M, and R stand for the properties of the composite, matrix, and reinforcement materials respectively, and N is a value between 1 and 1. The above equation can be further generalized beyond a two-phase composite to an M-component system, though composite stiffness is maximized when fibers are aligned with the loading direction, so is the possibility of fiber tensile fracture, assuming the tensile strength exceeds that of the matrix. When a fiber has some angle of misorientation theta, several fracture modes are possible. For small values of theta, the stress required to initiate fracture is increased by a factor of cos theta, 2. Due to the increased cross-sectional area, a cos theta, of the fiber and reduced force, F/cos theta, experienced with fiber, leading to a composite tensile strength of parallel/cos 2 theta, where parallel is the tensile strength of the composite with fibers aligned parallel with the applied force. Intermediate angles of misorientation theta lead to matrix shear failure. Again, the cross-sectional area is modified, but since shear stress is now the driving force for failure, the area of the matrix parallel to the fibers is of interest, increasing by a factor of 1/sin theta. Similarly, the force parallel to this area again decreases, F/cos theta, leading to a total tensile strength of my/sin theta cos theta, where my is the matrix shear strength. Finally, for large values of theta, near pi/2, transverse matrix failure is the most likely to occur, since the fibers no longer carry the majority of the load. Still, the tensile strength will be greater than for the purely perpendicular orientation, since the force perpendicular to the fibers will decrease by a factor of 1/sin theta, and the area decreases by a factor of 1/sin theta, producing a composite tensile strength of pip/sin 2, where pip is the tensile strength of the composite with fibers aligned perpendicular to the applied force. 76. The graph depicts the 3 fracture modes a composite material may experience depending on the angle of misorientation. Relative to aligning fibers parallel to the applied stress. The majority of commercial composites are formed with random dispersion and orientation of the strengthening fibers, in which case the composite Young's modulus will fall between the isostrain and isostress bounds. However, in applications where the strength-to-weight ratio is engineered to be as high as possible, such as in the aerospace industry, fiber alignment may be tightly controlled. Panel stiffness is also dependent on the design of the panel. For instance, the fiber reinforcement and matrix used, the method of panel build, thermoset versus thermoplastic, and type of weave. In contrast to composites, isotropic materials, for example, aluminium or steel, in standard wrought forms, possess the same stiffness typically despite the directional orientation of the applied forces and forward/or moments. The relationship between forces/moments and strains/curvatures for an isotropic material can be described with the following material properties: Young's modulus, the shear modulus, and the Poisson's ratio, in relatively simple mathematical relationships. For the anisotropic material, it needs the mathematics of a second-order tensor and up to 21 material property constants. For the special case of orthogonal isotropy, there are 3 distinct material property constants for each of Young's modulus, shear modulus, and Poisson's ratio, a total of 9 constants to express the relationship between forces/moments and strains/curvatures. Techniques that take benefit of the material's anisotropic properties involve mortise and tenon joints in natural composites such as wood, and pi joints in synthetic composites. Mechanical properties of composites. Particle reinforcement. In general, particle reinforcement is strengthening the composites less than fiber reinforcement. It is used to enhance the stiffness of the composites while increasing the strength and the toughness. Because of their mechanical properties, they are used in applications in which wear resistance is required. For example, hardness of cement can be increased by reinforcing gravel particles drastically. Particle reinforcement, a highly advantageous method of tuning mechanical properties of materials since it is very easy to implement while being low cost. 77, 78, 79, 80. The elastic modulus of particle reinforced composites can be expressed as where E is the elastic modulus, V is the volume fraction. The subscripts C, P and M are indicating composite, particle and matrix, respectively, is a constant can found empirically. Similarly, tensile strength of particle reinforced composites can be expressed as where Ts is the tensile strength, and is a constant, not equal to, that can be found empirically. Continuous fiber reinforcement. In general, continuous fiber reinforcement is implemented by incorporating a fiber as the strong phase into a weak phase matrix. The reason